Good day, everyone. Uh, Good day, and I do believe we are all doing fine. But in this video tutorial, I'll be taking us through how we can use proteus simulation software to run common emitter transistor configuration in our proteus simulation software. So the manual is what we are seeing on the board. The aim of the experiment is we are trying to configure transistor in a common emitter configuration. Like we know, there are three ways of configuring a transistor in the circuit: the common base, common emitter, and the common collector. Simply put, in the common emitter configuration, the emitter terminal is common to both the input and the output section. This is the emitter terminal, and this is the input section. The input parameters are IB, the current through the base, and the voltage between the base and the emitter terminal, while the output section is the current IC, current through the collector, and the voltage between the collector and the emitter terminal. So that is why it is called common emitter configuration. So in this experiment, basically what we will be measuring for the input characteristics, because in this experiment the experiment is divided into two different sections. The first section is the input characteristics section, then the second one is the output characteristics section. So in the input section, we will measure the input current and the input voltage at a specific constant output voltage VCE. Then when we are done with that, we go to measure the output current and the output voltage at a specific base current. So that is how we run the experiment. So the table that is expected, table of observation from this graph is going to look like this. For the input characteristic, we are using two specific output voltage value at 0 volt, and I think there was a modification that I did at 1 volt, at 2 volt, and at 4 volt. So you may because we want to have like three different curves: at 1 volt, at 2 volt, and at 4 volt. So we measure the voltage, the input voltage VBE and the input current IB at a constant output voltage of 1 volt. When we are done with that, we go to the second one at a constant output voltage of 2 volt. We measure VBE and IB. Then at 4 volt, we are going to do the same thing. So if you are configuring this table, you make a provision for an extra column to accommodate that 4 volt. So that is that. So without wasting much time, let's launch the proteus. This video also actually assume that you have already installed the proteus on your system. So having installed the proteus of simulation software, you arrange the circuit like this. Now if you look at this circuit and the circuit diagram in the manual, they are the same. The only thing that you are seeing that makes this one look a bit more complex is that we have added all those meters, the multimeters, to measure the different current and the voltages. So as you can see on the board, on the screen, we have seen the voltage to measure the output, that is the VCC. This VBB. This is VBB. So let me try to give them a name. This is VBB. So let me assign VBB. So this is voltage VBB, and this is VCC. This is VCC. So now I have added a potentiometer here. That is the name of the potentiometer is port HG, interactive potentiometer, that allows us to vary the value of this voltage supply. And this is one is a V source. I've seen it here. If you click on it, it will drop. And to patch off circuits in the proteus is very simple, just a matter of connecting the end of every component. Once you click this, let's say I want to connect these guys together, you just take your cursor to this and it will become highlighted. Then you drag it. Once you click and you drag, you can easily connect. So connecting something in the connecting our circuit on proteus is very, very simple. So just drag and drop. So that is how we have wired this. So we want to start the experiment now. So we don't need this. Let me take them off. So having connected everything, you start your experiment from 0 volt, VBB of 0 volt. That's why use this point to adjust the value of this voltage. So let's simulate so that we can actually adjust it. We want this to have a value of 0 volts. So you begin to click. So let me try to make this a bit bigger. So let me make it a bit bigger, so that's okay, so that every one of us can see it. I think we can see it better now. It's a bit more bigger now. We can see it well. So I want to start from 0 volts. When this is 0 volts, what is your input current and what is your voltage? The input current is 0, the output current is 0. So I've prepared an Excel sheet where I'll be recording my table of value. I've already done the experiment. So when VB is equal to 0, input current is 0, output voltage, input voltage is 0, input voltage is 0, and input current is 0. So at VBB equals to, so you go to the experiment again, you now begin to use this knob to adjust the value. At 0.12, you see the input voltage is 0.12, but mind you, this value is no longer at 1, so we have to use VCC. Each time the something want to leave the set point, you use this value to set it back. So use this one to set it back. Now, as it is obvious we can't get 1, so 0.96 is what is close to 1, so you leave it there. You can now take your reading 0.12 and 00 for the current. So you go to the Excel and record 0.12 for VBE and 0 for IB. So the same thing, you continue like that, even at 0.24 the same thing, at 0.36 the same thing, 0.48 the same thing, 0.6 you started seeing current IB flowing. But before you can take your reading, try to set this thing back to 1. Which one is closer? 0.92 and 1.04. So let's see the margin calculator. So let me pick up a calculator here so that we know which one we are going to set it for, since we can't get 1 exactly. So if we cannot get, so 1.04 minus 1, that will give us what? 0.04. that's the margin, error margin there. So if we use the other one, the other value, the other value apart from 1.04, 0.92 is the value below 1. That's 1 minus 0.92. What do we get? 0.08. So definitely it is better, we are safer when we use 1.04. We are closer. The error of margin, the margin error there, so this is assumed to be 1. So you take your reading. The base current is 0.14 microamps and the voltage is 0.59. You go to the Excel sheet and at 0.6, what do you see? 0.14 microamps, then 0.59, 0.14 microamps at 0.6, 0.14 microamps. So you record it 0.14 at 1 volt, 0.14 microamps. Then the VB is what? What's our VBE? Our VBE is 0.59. So 0.59. So that's how you continue the experiment. You take all the readings. When you get satisfactory number of points, then you go back to this and set the voltage at 2 volt. So let's try to set this at 2 volt. Remember to always take this thing back to the lowest value. So set this at 2 volt. At 2 volt. At 2 volts. 2.04 is 1.92. So 2.04 is closer to 2. So you take the readings at 2.04. What do you see? 0.12, 0. So no change. At 0.24, the voltage still appear there, no current here. At 0.36, no current. At 0.48, no current. At 0.59, at 0.59 here, that is 0.6 VBB. then VC is 0.59, this one is 0.14. So we go and record the value at 0.59. we go and record the value. So when you have done that for 0.2, you do the same thing for voltage at when VC is equal to 3. So you're going to do it like that. So I've already recorded this value. So when you are you can at your own layer take enough samples, enough measurements, and when you are done, you can now go and plot the graph. How do we plot the graph in Excel? It's simple. Just try to select every values here. Select everything. When you select everything, then you go to insert. You click on insert. When you click on insert, go to chart. Click on the drop down, go to more scatter plot. From there you can now click on scatter plot with straight line. So click on scatter plot with straight line, you get something like this. You can see it is still similar to what I got the other time. So you can now maximize it. You can give it a name. You can type the title of the experiment, input characteristic curve, just like what I've already done here. So I will make use of the one I'm working with so that we can now make our analysis. So we have done the input characteristic curve. So now from the input characteristic curve, you can now find the input impedance, that is the H parameter of the system. Simply let's quickly find the H parameters. Now from the manual or from the test, whatever textbook we are using, I will try to provide a link to download this laboratory manual for users, for viewers. I will make an avenue for us to download the laboratory manual. So after you have plotted the graph, you want to find the input characteristic, you want to find the input impedance, that is HIE, which is giving us change in VBE over change in IB. HIE is change in VBE over change in IE. So from the graph, you can easily find that. Just like the normal way we do our mathematics, we find the slope of a curve in mathematics, y2 minus y1 over x2 minus x1. So I've tried to write the formula down here. So let's take this yellow. You can see that this is VB at VB is equal to 1 point. So when we take this guy at this point, what is the value of on the x-axis, what is the value on the y-axis? It's already written there. Once you take your cursor to any point on the graph, on the curve, you see that the coordinate of that particular point will be revealed by your cursor. You are saying 1 on the x-axis, 233 microamps on the y-axis. So if you trace it, you see that this is 1. So that means our y2 is 233 microamps, our x2 is 1. Then if you take, let's say you are using this point, for example, now this is second point, you have seen it as 0.8, 55.8, that is 0.8 on the x-axis and 55.8 on the y-axis. So if you go to this place, y2 minus y1 over x2 minus x1, that will be your change in VBE over change in IC. So from there, 1 minus 0.8 over 233 minus 55.8 will give you 0.2 over 177.2, and 0.2 over, now don't forget the current is in microamps. So 177.2 converted to microamps will give you 0.0001772. By the time you do everything, you get your HIE to be 1128.6 ohms. Now when you look at this value, you see there is a very high value of resistance, and that is a very high input resistance. So the essence of this is that every transistor configuration, or let me say transistor amplifiers, must have high input impedance, so that to prevent to maintain the stability of the system. There are many advantages, but system stability, high response, and other benefits like that. You can read up about input impedance, advantage of high input impedance for transistor amplifier, So that will be all for common emitter, input characteristic of common emitter. So don't forget, we are not done with the input parameters, but I want us to go and check the second video where I discuss about the output characteristic curve. So when we're able to get the two curves, so we can now extensively solve and get the 4 parameters, because the other values, the other parameter, the other hybrid parameter values, we need the output characteristic curve to be able to do that. So that will be all for now. If you have any questions, if you have any area of this video that is not clear, please kindly send me a message on the email that is attached to this video. Thank you very much. Please, I will appreciate if you can just click on the notification channel button and subscribe to this YouTube channel for more educating videos. Thank you.